Welcome everyone to the distributed algorithms session, a brief session right before lunch. We do want to get started promptly, so I want to get things going right away. Our first talk is Logstar Round Game Theoretically Fair Leader Election by Ilan Komorgatsky, apologies. Shinichiro Matsuo, Elaine Shi, and Kei Wu, who will be giving the talk. So welcome, Kei. Thank you.
Thanks for the introduction. So you probably saw on the schedule log question round, game theoretically fair leader election, and here's the answer is Logstar Round. And this is a joint work with Ilan Komorgatsky, Shinichiro Matsuo, and Elaine Shi. So Ilan and I need to decide who will go present this paper. Both of us want to go enjoy the beautiful beach in Santa Barbara, so we decide to toss a random coin. If the output is 0, Ilan will present the paper, and if the output is 1, I will present the paper. You probably already know the result, but let me tell you the whole story. Since we were in different cities, we decided to do Blom's coin toss on a blockchain. If you're not familiar with blockchain, you can just think of it as a public bulletin board. So we first each toss a random coin, and we post the commitments of these 2 random coins on a blockchain. After that, we each open our random bit. Let's say my random bit is 0 and Ilan's random bit is 1. So the output is just the XOR of these 2 random bits, which is 1. So I win, and here I am. However, Ilan really wants to go enjoy the beautiful beach in Santa Barbara. So there he is. After I open my bit 0, he knows that he's going to lose the game if he opens his commitments. So what if he refused to open his commitment? In that case, I just automatically win, and the output is still 1. So this is the famous Blom's coin toss protocol, and it guarantees that a strategic player like Ilan cannot gain benefit for himself, and an honest player like me will not be harmed. So formally, in a coin toss protocol, our goal is to toss a uniformly random coin. And the traditional notion of fairness considered in crypto literature is called strong fairness, which requires that a strategic player cannot bias the output towards either direction by more than a negligible amount. So if we have honest majority assumption, we can just use secure multi-party computation to achieve this strong fairness. However, Clevin showed in 1986 that this strong fairness is impossible to achieve against half corruption. Indeed, even in the Blom coin toss protocol we just see, Ilan can always bias the output towards 1 by refusing to open the commitment. So the fairness achieved by Blom's coin toss protocol is more of a game theory favor. It guarantees that first, a strategic player cannot benefit itself, and second, an honest player cannot be harmed. So now that we've seen this Blom's coin toss protocol guarantees game theoretic fairness for 2-party. What about multi-party? When it comes to multiplayers, the problem becomes a leader election. Now let's say we are electing our next crypto PC chair from Shafi, Dan, Bren, and Yale. So our goal is to elect a uniformly random leader, and the utility is just that winner takes all. The elected leader will gain utility 1 and everyone else gain utility 0. Although there are a lot of work to do, but everyone wants to serve our community, so everyone wants to be elected. Dan and Brent, they're so eager to be elected that they form a coalition and they want to bias the output towards their favor to increase their joint utility, where the joint utility of a coalition is 1 if the elected leader is inside the coalition. So formally, in a leader election protocol, our goal is to elect a uniformly random leader if everyone behaves honestly. And the game theoretic fairness notion we considered for a leader election protocol is slightly different. Here, we want that first, no coalition can increase its expected utility. And second, no coalition can harm any innocent, honest individual. So if we have a game theoretically fair leader election, then the honest behavior actually forms an equilibrium. So one thing is, why do we care about this game theoretic fairness? Because strong fairness, as we saw, is impossible to achieve against majority-sized coalition. Yet we still want some meaningful fairness that is achievable against majority-sized coalition. In decentralized applications, game theoretic fairness is actually the de facto approach, and we actually have many game theoretic design in practice, although sometimes without provable security, but this is the notion that people want to have. Now you may ask, why should I care about corrupted majority? Why can't we just assume we have honest majority and we only need to do secure multi-party computation? This is because in decentralized applications, many pseudonyms may be controlled by the same entity. And these pseudonyms will coordinate with each other, and they may deviate from the protocol to gain benefit. It is very likely that these pseudonyms form a corrupted majority. And this is actually a real world attack where someone faked a lot of identities and faked a DeFi ecosystem to juice value from cryptocurrency. So in this work, our focus is to achieve game theoretic fairness against corrupted majority. Now let's back to our PC cherry election. The folklore way to do this is called the tournament tree protocol, where each pair of players duel with each other with Blum's coin toss, and the winner duel with each other again until we have a leader. So the game theoretic fairness in tournament tree protocol is guaranteed by Blum's coin toss. However, it takes log n rounds for general N players. So a natural question to ask is, can we reduce the round complexity? Can we achieve fair leader election with less than log n rounds? Here are both bad news and good news. The bad news is that if we insist on perfect fairness, and if we insist on ideal commitment model where commitment is the only crypto primitive we can use, then log n rounds is necessary. However, if we are willing to relax our fairness notion to 1 minus epsilon fairness, which requires that first, no 1 minus epsilon fraction corruption can increase its expected utility by more than epsilon fraction. And second, no 1 minus epsilon fraction corruption can harm any honest individual by more than epsilon fraction. And moreover, if we're willing to use other crypto primitives like zero knowledge proof, then we can do log n rounds for epsilon to be small o1. So here's a clear trade-off between the round complexity, the fairness parameter, and the size of a coalition we can tolerate. For log n rounds, we can achieve perfect fairness against arbitrary sized coalition by tournament tree protocol. For log n rounds, we can achieve 1 minus small o1 fairness against 1 minus small o1 fraction corruption. And this is given in CCWS 21. But what about smaller round complexity? Can we achieve meaningful fairness with less than log n rounds? In this work, we give an affirmative answer. So in this work, we give a log star round leader election that achieves 1 minus small o1 game theoretic fairness against 99% corruption. So basically, our leader election is round efficient, and it achieves good fairness, and it can tolerate arbitrary large constant size fraction of corruption. In the paper, we also give a fully parameterized result about the trade-off between round complexity, fairness, and the size of a coalition we can tolerate. But in this talk, we're just going to focus on the log star round result. Okay, now let's see how we get our fair leader election protocol. The technique used in previous work in CCWS 21 does not directly generalize to smaller round complexity. So we built our leader election protocol from scratch. And we start from a strawman solution, which is a variant of Vegas lattice bane protocol. We'll see how it fails to achieve the fairness, and we can fix it with a commit and open lattice bane. This is pretty much our final protocol, except that it still has a little issue to fix. And after fixing that, we got our final protocol. So in the rest of the talk, we'll walk along this path and see how we get our final leader election protocol step by step based on our strawman solution. First, let's recall how Vegas lattice bane works. He starts from n players, a population of n, and then he chooses a preliminary committee of polylog n size. Then he chooses a smaller committee of polylog n size from the preliminary committee, and he does this all the way till there's only one player left, which is our elected leader. So in total, this takes log start and rounds of committee election, and each committee election takes constant rounds. So the round complexity is log star n. In our strawman solution, we also run several rounds of committee election as in biggest lattice spin protocol. The only difference is that we stop when the committee size reaches roughly 2 to the log star n. We stop here and switch to time entry protocol to elect a leader directly from this 2 to the log star n committee. I'll talk about the reason of stopping early and switching to time entry protocol later. So in this strawman solution, we run no more than log star n rounds of committee election, and we run a log star n round time entry. And in total, the round complexity is still log star n. So now the remaining thing is really just how we run this committee election. As long as the committee election is fair in each step, then our final leader election is fair. And by fair committee election, I mean that a corrupted coalition cannot increase their fraction in the committee by too much, and they cannot harm the probability of an honest player being elected into the committee by too much. So from now on, we'll just focus on this one step of committee election. And as a reminder, we are focusing on 99% corruption. Now say we have M players, and these orange players are just corrupted players. And these gray players, they're honest. To elect a committee of size C, we let every player to uniformly randomly choose a bean from N over C beans. And the players in the lightest bean will be elected as the committee. So by turn of bound, the number of honest players in each bean should concentrate around its average, which is 1%. That means with a large probability, every bean should contain at least roughly 1% C with times 1 minus epsilon, a small slack number of honest players. And by pigeonhole principle, the lightest bean definitely contains no more than C players. So together, this means that no matter how the corrupted player distribute themselves, the fraction of corrupted players in the lightest bean must be roughly very close to 99%. So in this drama solution, it actually guarantees that a large coalition cannot benefit too much with a large probability. And this large probability is actually the reason we have to stop early and switch to time entry protocol. Because if we run the committee election as in biggest lightest bean all the way till the end, then in the last few rounds, we're electing a very small sized committee from a very small sized population. And this probability becomes a constant probability with respect to N. And that means in the last few rounds, the large coalition can gain benefit with constant probability, and that ruins our fairness requirement. So we have to stop early while this probability is still reasonably large, which is 1 minus small o1, and we switch to time entry protocol, which preserves the fairness for us. So now, the strawman solution guarantees that a large coalition cannot gain benefit too much. But how about a small coalition? Surprisingly, in this strawman solution, small coalition can gain significant advantage. To see how this works, let's say there's only one corrupted player. So it will wait until honest players to make their bean choice, and then it will decide its own bean based on honest players' bean choice. Now let's say the honest players distribute themselves as in the slides. Then a rational, smart, corrupted player will definitely choose the last bean. And after it put itself into the last bean becomes the lightest bean, and it is guaranteed to be elected into the committee. In general, this attack can be performed as long as the second lightest bean is too heavier than the lightest bean, which happens with a very large probability. So to fix this problem, we come to our second try, which is commit an open lightest bean. So this corrupted player can perform this attack we just described simply because it can choose its own bean based on honest players' bean choice. So we just hide the bean choice of honest players by commitments. Now we let every player to commit to its bean choice first. And now this corrupted player has to commit to a bean choice which should be independent from honest players' main choices because the commitments hide the honest players' main choice. Now, after the honest players open their bins, this corrupted player can either choose not to open or open to an incorrect bin, in which case it will be immediately kicked out and it gains no benefit. Or it has to open to the bin it commits to, which is independent from honest player's main choice. So in commit and open, this corrupted player can only hit the lightest bin with probability C over N, which is exactly what we want. So now with this commit and open lightest bin, we get no collision can noticeably increase its expected fraction in the lightest bin, as long as it's no more than 99% corruption. However, as I mentioned to you, this is almost the final protocol, but it still has a remaining issue that a collision can still harm an honest individual. Let's say this black player in the circle is an innocent, honest player that the collision wants to target because he's too smart. So to harm this honest individual, the collision can just distribute themselves as even as possible into the bins. And then they wait for honest players to open their bin choice. Now they see that honest player, this honest target, chooses bin 3. Now they choose which commitments they want to open based on honest players' openings. To exclude this honest target from being elected, what they can do is they'll refuse to open these 2 commitments in the first bin. And now, as we mentioned, they'll be kicked out. And after they're kicked out, the first bin becomes the lightest bin, and the players in the first bin are elected as the committee. And there's no way for this honest target, this black honest target, to be elected anymore because the coalition tries so hard to exclude it. So we need to fix this problem, and we come to our final protocol. Due to the time constraints, I'm only to talk about a very high-level idea of this fix. So we basically use a virtual ID technique introduced in CCWS 21. We let every player to randomly choose a virtual ID for themselves. And we use this virtual ID to do the commit and open lightest bin. Now the coalition only get to see the bin choices of these honest virtual IDs. So as long as the mapping between the real identity and the virtual ID is hidden from the coalition, then they doesn't know who should I exclude, which virtual ID should I exclude. They doesn't know that. And this mapping is hidden by commitments. However, it's not just this easy that we can hide the mapping by commitments because we're in authenticated broadcast channel. And we know the identity of the sender for each message. So when the honest target opens his bin choice based on behalf of his virtual ID, he has to send this message. Virtual ID 3 chooses bin 3. And once it posts this message on the broadcast channel, the coalition immediately knows, oh, you're behind virtual ID 3, and you choose bin 3. We know how to target you. And they can perform the same attack as before. So to get rid of this problem, we actually need to run this commit and opening an anonymous broadcast channel, which hides the identity of the sender of each message. Assume that if we have this anonymous broadcast channel, then the coalition only get to see a message, virtual ID 3 chooses bin 3. But the coalition doesn't know who sent this message, and they doesn't know who is behind virtual ID 3. And so they cannot target an honest individual anymore. And in our paper, this anonymous broadcast channel is instantiated with bounded concurrent zero knowledge proof. So now this is our final committee election protocol. It is commit and open with virtual ID, the anonymous broadcast channel. It guarantees that first, no coalition can noticeably increase its expected fraction in the lightest bin, which is guaranteed by commit and open. And second, it guarantees that no coalition can noticeably harm an honest individual, guaranteed by virtual ID and anonymous broadcast channel. So to wrap up, in this paper, we give a game theoretically fair leader election that runs in log-star rounds. And also we give a fully parameterized result for a game theoretically fair committee election. And there are some interesting open questions left in this work. The first one is that in the previous work in CCWS 21, their leader election actually satisfies a stronger fairness notion, which is called sequential notion of fairness. it guarantees that at any point in the protocol, given the current information, the collision doesn't have incentive to deviate. But our protocol does not satisfy this wrong notion. So it would be interesting to see if if any meaningful result is achievable with less than log-log-n rounds for the strong sequential notion of fairness. The second one is that in this paper, we only give the upper bound. So it would be interesting to see if there's any lower bound on the round complexity necessary for achieving 1 minus epsilon fairness. And the third is that we do not claim practicality of our protocol. So it would be interesting to see if there's any practical variance of our protocol that is implementable in real world applications. And that completes my talk. Thank you.
Thank you, Kay. Any questions?
Thank you for the talk. So I have two questions, actually. The first one is, if you're assuming synchrony and crypto, why can't you use something like time lock puzzles to do this?
Oh, because we're not assuming we're in the timing model. Like we're just considering synchronized. We are in synchronized round model.
So how
like
do you implement
messages.
that without time?
Sorry?
How would you implement this without time?
How would you
implement a synchronous model without having a notion of time?
So we're just assuming that our protocol runs in the synchronized round. So like
It's lockstep, but it's not synchronized.
it's in synchronized channel. So
But how do you implement this without synchrony? Maybe we can discuss it offline. But actually, my other question relates to the first one. So if the network is completely asynchronous, is there anything known or?
No.
Okay.
So like our work focused on synchronous network,
Okay.
and it would be interesting to see if there's any work that can be done in asynchronous channel.
But then probably FIGA's protocol doesn't work anymore, because then you can.
Yeah, I think yeah.
Okay, thank you.
Thank you.
Well, the first very small question is just so for commitments, do you need non-malleable commitments or just regular commitments for the
So-
commitments that you use?
So
In
the
Blum's protocol?
yeah, so like we have two commitments. Step one is the commit and open, where players have to commit to their main
Right.
choice.
Yeah.
There we need non-malleable commitments. And the second is actually for the instantiation of the anonymous broadcast channel, we need commitments. And there we just need normal commitments that is perfectly binding and computationally high.
Yeah, because I saw some non-malleability things, but you're saying, yeah, good. So you do use non-malleable commitments.
Yes, we do use non-malleable commitments.
And in terms of the assumptions, I actually forgot what is the latest on non-malleable commitments. I think one-way functions, but maybe isn't. But in terms of assumptions, like also for concurrent zero knowledge, what are your final assumptions in terms of like the simplest possible assumptions? Can you base everything on one-way functions, or what's the final assumptions?
We need trapdoor permutation and collision resistant hash for the bonded concurrent zero knowledge proof
I see.
used in our instantiation of the anonymous broadcast channel.
And just in general, like for example, even non-malleable commitments are they interactive? In general, all your primitives are interactive, so and it's okay to use interaction, but it's like small number of rounds, so it's a constant.
Yeah.
So I see.
Yeah.
Okay. Well, thank you again, Kay. So the second and final talk of this short session will be Gossiping for Communication Efficient Broadcast by Eurostimos, Julian Loss, and Charlampos Papankos. Papamantos, something, sorry. And giving the talk.
Thank you very much. So yeah, I'm Yorgos. It's nice to be here today. I'm going to talk about gossiping for communication efficient broadcast. And this is a joint work with my amazing collaborators, Julian Loss and Babis Papamantou, my advisor. Julian is at CISPA and Babis is at Yale. So let's dive in. So broadcast is basically the problem where end parties want to communicate. A designated sender wants to send its input value to all these end parties and broadcast its value to all these end parties. However, the sender might be dishonest and in this case might send different values to different parties, but still all honest parties want to agree eventually on the same output value. In the authenticated broadcast setting, it's basically broadcast with the additional use of the public key infrastructure or PKI. This can be a bulletin board PKI or a trusted PKI. In the bulletin board setting, basically parties post their own keys in a bulletin board, whereas in the trusted setting, there's a trusted authority that issues the keys and distributes them among the parties. And therefore, because of the access to PKI, each party can sign messages with their own signature. So we can see this via an example. Assume now there are these 5 parties. The designated sender is the king, and he wants to send his message to all other parties in the protocol by using the broadcast protocol. And still, some parties might be dishonest. However, we want the properties that at the end of the protocol, all honest parties will agree on the same output bit. And if the sender is honest, all honest parties will agree on the same bit. So authenticated broadcast comes in many flavors, depending on several factors, such as whether we have synchronous or asynchronous communication between the parties, the number of corruptions, whether we're in this honest or dishonest majority setting, the setup assumptions, as we mentioned already, we can have trusted setup or no trust at all, and whether the adversary is static or adaptive. Basically, a static adversary can corrupt parties only before the execution of the protocol, whereas an adaptive adversary can corrupt parties dynamically during the execution of the protocol. So we use different metrics for the broadcast protocols. The first one is the communication complexity, which is the total amount of information exchanged between parties throughout the execution of the protocol, between honest parties. And it's also the round complexity, which is the total number of rounds that it takes for the protocol to execute. In our setting, for this work, we are in the synchronous communication and dishonest majority, where the adversary can corrupt up to a fraction of as many parties as he would like. And if we also exclude trusted setup, the state of the art in this setting is Dolev-Strong paper with a cubic communication to the number of parties in the protocol. So in this work, today I will show how we achieve to have authenticated broadcast with quadratic communication complexity using only bulletin board PKI, thus improving the Dolev-Strong by an order of n. And we will also introduce gossiping and converge to new techniques in this area. And we will show parallel broadcast. I'll explain later what parallel broadcast is. We'll show parallel broadcast protocols with cubic communication using bulletin board PKI and quadratic communication using the trusted PKI setting. So first of all, let's dive into Dolev-Strong and understand it a little bit better. This is a very straightforward protocol. In the first round of the protocol, the designated sender sends its own message signed by its own signature to all parties. And in every other round, up to t+1, where t is the total number of corruptions the adversary can have, each party checks whether it received a new valid message. Valid here in the sense that a message must be accompanied by at least as many signatures from distinct parties. And if it does receive a new valid message, it adds its own signature to the message and sends the message accompanied by all the signatures to all parties in the protocol. So as you can see, Dolev-Strong achieves an authenticated broadcast for any number of adaptive corruptions. It's deterministic and takes order of n many rounds, and it only assumes bulletin board PKI. But the total communication complexity is cubic to the number of parties, as we already mentioned, and we would like to see if we can improve that. So to improve that, we thought whether there is redundant information shared between parties throughout the protocol. And you can see that because all parties will send to all other parties, therefore incurring already a quadratic communication. And the largest message that the party might send to all other parties is in total order of n, because it will be a message accompanied by an order of n many signatures. Therefore, the cubic communication seems to come from the fact that Dolev-Strong uses some redundant information. And basically what parties want to achieve with sending is that they want to observe the information between each other, exactly the same information between each other. But this can take less than cubic communication to be achieved. In order to do so, what we think is the following. Every time a party has to send to another party, it will first ask itself, do I send to this party? It will flip a coin to answer, and if the coin lands heads, then it will send, otherwise it won't. This is basically the main idea of gossiping. Each honest party randomly picks a few other parties to send to. And of course, if it just did that, then it wouldn't achieve propagation of the message to all parties. Therefore, we need to have an additional order of n log n many rounds to achieve propagation to all parties. So we can think of it via an example. Imagine the designated sender S here wants to send a specific message to all parties. Some of the parties might be corrupt. And at some round alpha, the sender begins to send the message, picks a few random parties to send the message to, and they in turn pick a few other random parties to send the message to, etc., etc. And after a very small amount of rounds, the message is being sent to everybody. This is the basic idea of gossiping. So we use this idea of gossiping in collaboration with the Dolev-Strong protocol to achieve an improvement. Our protocol works as follows. It follows very close to Dolev-Strong. In the first round, exactly the same happens. The designated sender sends the message to all other parties. But then, for every round, when a party wants to send a message, instead of directly sending the message to everyone else, it will gossip the message via log n many rounds of gossiping. So the result is that we achieve authenticated broadcast for any fraction of static corruptions, which is a randomized protocol. It takes O of n log n rounds in the way that I explained here, but actually in our paper, the protocol achieves O of n rounds, exactly the same as Dolev-Strong, and it assumes only bulletin board PKI. The total communication is O of n squared. So if we compare our protocol to Dolev-Strong, we can see that it is actually improved in communication, but it has the flaw that it is not secure against an adaptive adversary. It is easy to see that because an adaptive adversary can wait during the propagation of a message in the gossiping phase. And once it observes the communication pattern between parties, and it observes that only a few parties receive the message, it corrupts all these parties, breaks the propagation of the message, and therefore breaks the security of the protocol. So back to our motivation, we would like to think if we can combine the gossiping technique with some other idea to achieve security against adaptive adversaries. It is the case that many times when we actually need broadcast in practicality, we need it in another sense, where all parties want to send information to all other parties in the protocol. This is the case in many MPC protocols and verifiable secret sharing schemes. So we introduced the notion of parallel broadcast. This is an already known notion, but we will use it in our protocol in a non-black box manner. In parallel broadcast, we have again n parties, t of which might be corrupted, but now every party will act as a sender. Every party has some input value and they want to send it to all other parties in the protocol. So every party defines a slot in the sense that a slot is basically the authenticated broadcast for this specific sender. And each party, in the end, will output n many values, one per slot. The properties we want are still the same. We want for every honest slot, all honest parties to output the sender's input value. And we want for every slot, all parties to agree on the same output value. So again, we can see it schematically now. Instead of having one designated sender acting as a king, we have 5 generals. They all want to communicate between each other. They will use a parallel broadcast protocol to achieve the properties that we want. However, still some of them might be corrupt. So The trivial solution that is actually, because parallel broadcast hasn't been studied very much, it is the only solution that's been applied so far. The trivial solution is to use the best broadcast protocol for the underlying assumptions that we want, n times in parallel, once per slot. And therefore, if there is some specific communication of the underlying broadcast protocol, say C, the overall communication would be O of n times C. And we also care for the amortized communication, which would be whatever communication is incurred over C, because we have n authenticated broadcasts, one per slot. The question, though, is if we can do better than that. And as I already said, we will introduce, first of all, Converge, and so two parallel broadcast protocols that indeed do better. So Converge follows from the following. We observe that in parallel broadcast, parties have to propagate at least order of n messages in total. So they have to propagate, if you think about it, since there are n many slots and n many parties, the total communication, even with the information theoretic model, would be O of n squared. And we can therefore combine this inherently larger amount of information with gossiping to achieve parallel broadcast both more efficiently and also securely against adaptive adversaries. The way to do that is the following. Observe that before, in the gossiping, parties would just pick some other parties at random and send the messages to them. Now, however, we have every party sending many more messages per round. So like in gossiping, if this party picks recipients at random for every message, in the end, with high probability, all parties will receive approximately the same amount of messages. We can increase the security by using covered traffic and ensuring that all parties will receive exactly the same information in the eyes of an adaptive adversary. And that's what Converge will do. In this case, the adaptive adversary will not gain any advantage by observing execution of the protocol, and therefore the protocol will be adaptively secure. So let's think of it via an example. Imagine that the party, the Charlemagne, wants to send 5 messages to all other parties in the protocol. So every list here corresponds to what its corresponding message party. So L1, for example, corresponds to party P1, L2 to party P2, etc. And every list contains the messages that the party will receive from a specific sender. So the sender, what will do is it will pick its message and randomly select a few parties to receive the message. So for the first message, it will randomly pick some parties, for the second, the same, etc., etc. At some point, it will fill the lists with this random process. And the list will already contain almost the same amount of information. But what we also do is we add garbage messages to all the lists so that they all reach the same exact size. After that, we will also encrypt the lists so that only the recipient can read them. And at this point, the adversary basically, if it observes the communication pattern of the protocol, it will observe exactly the same communication information for every recipient. Therefore, the adaptive adversary gains no advantage by observing the execution of the protocol. With this in mind, we have our first PBC protocol, which is in the bulletin board. It is very simple, actually. Again, in the first round, every party will send its own message signed by itself to all other parties. And then for every round, again up to T+1, there are 2 stages. In the first stage, again, every party will check whether it received a new valid message. Valid in the same sense as before, a valid message is accompanied by many signatures. If it does so, it will add its own signature to a set of signatures that it needs to propagate to all other parties. And in the second stage, it will use Converge, the idea of Converge, to propagate this set of signatures to all other parties. Therefore, after this stage, all other parties will receive the same signatures that this party has observed, and can also decide whether a message is valid or not in the next round. This very simple protocol achieves an improved communication complexity. The reason for that is the following. We can think about it. So we have order of n many rounds, and each round calls Converge. The total amount of messages that a party might need to propagate through Converge is order of n squared. Therefore, we would have n parties propagating increased amount of communication of 1/3 per party. Instead of doing that, what we achieve in our protocol is that we minimize the amount of times a party will propagate the same signature. Therefore, we make it constant, and therefore we achieve improved communication of O(n) cubed, which is, if you think about it, it's amortized O(n) squared per broadcast. So what we basically achieve is authenticated parallel broadcast, again for any fraction of adaptive corruptions. This time it's adaptive. The number of rounds is O(n) log n, so we have a slight increase in the number of rounds. Again, we only use bulletin board PKI. And the total communication is, as we said, O(n) cubed, which is amortized O(n) squared. Similarly, we have another result in the trusted setting. So for the trusted PBC, we modified a single sender broadcast protocol by Chan et al., which appeared at PKC of 2020. This protocol is committee-based. Due to the lack of time, I will not go into many details with this protocol. However, the basic idea behind it is that in every round, when we need message propagation, we, instead of sending to everybody, we use Converge. So this protocol achieves, again, authenticated parallel broadcast for any fraction of adaptive corruptions. It's also adaptively secure. It's randomized and takes all kappa times log n rounds, where kappa is the security parameter. And however, it assumes trusted PKI. And the total communication is even more improved. It's O(n) squared, which means O(n) amortized. And we can compare our protocols to the state of the art. We can see that in the bulletin board setting, all protocols in the same setting, meaning Dolev strong, basically, because it's the only one that takes up to as many corruptions, and it's in the bulletin board. All protocols fare worse, and actually our bulletin parallel broadcast protocol is even improved in comparison to our single sender protocol, because it achieves adaptive security. And also in the trusted setup, we improve the amortized complexity in comparison to the Chan et al. Protocol by a factor of n. Therefore, our contribution from this work include gossiping, introducing gossiping and Converge, and 3 state-of-the-art protocols. A parallel broadcast protocol which achieves quadratic complexity using trusted PKI and is secure against an adaptive adversary who can corrupt up to any fraction of parties. Another parallel broadcast protocol which uses bulletin board PKI and is again secure against an adaptive adversary and achieves cubic communication complexity. And a single sender broadcast protocol in the bulletin board setting, but only against a static adversary. You can corrupt up to as many parties again. Thank you very much.
Thank you, Yoros. Any questions?
Hello, thank you for the talk. A question about the big O notation. Do you have an idea on how many how many parties this becomes competitive compared with other protocols? For example, let's say if you have 16 parties, would this already be good to use?
That's a good question. No, when there is a small amount of parties, it is, if you think about, let's say the specific example that you gave, we have, let's say, 16 parties. And there is an adaptive adversary who can corrupt dishonest majority and can corrupt, let's say, 10 of them. There are already very few honest parties to communicate between each other. So if you just send a logarithmic amount of information, it would be very hard to even hit an honest party. So actually, because of this, our protocol, as it goes closer to a fewer amount of honest parties, it goes closer to the Dolev strong, actually. So there is a factor over there which depends on the fraction of dishonest parties and the total amount of parties. I think right now the protocol does not operate that well in practical settings, and that's actually a very good question for further work. So no, I would say that we need a much larger amount of parties to operate better.
Hi, thanks for the talk. I wanted to ask, why does the parallel broadcast work against adaptive corruptions while the original protocol or like the single broadcast seem to only work against static corruptions?
Yeah, sure. I can explain it further. So in a single broadcast, an adversary can observe the communication pattern between parties, and this communication pattern gives you information. This is because you have only one or two messages to propagate, and therefore at the beginning of gossiping, you will propagate these messages to at most all of log n many parties, let's say. The adversary can observe which parties receive messages, corrupt them, and therefore stop the propagation of a message. In the parallel setting, because you have many more messages to propagate, you can use these messages and combine them to hide the communication pattern. Therefore, an adversary will observe, as we explained in the propagate process, the adversary will observe every party receiving, like I am to send to at this round. I will send, eventually I will send a list to all parties, and this list could be of same size, constant size, but of the same size. Therefore, the adversary, even if it's adaptive, will observe a communication pattern that's indistinguishable between parties, and therefore it cannot decide any better than randomly. The reason behind this is that in parallel broadcast, inherently you have more information to propagate, and therefore you can use this information to improve in terms of security.
Okay, thanks. That makes sense.
Any other questions? Okay, well, I think you're standing between these good people and their lunch, so we will thank you again.